Mm, Hello, students. Good afternoon to all of you. So, you are most welcome in the Department of Chemistry, LNT College Multimedia Studio. So, in this next video lecture, we will actually focus on application of cryptand and cryptates. So, in the previous lecture, you have studied the structural features of cryptand and its complex structure, that is what we call cryptates. So it has a various structural aspects, and they are selectively uh, able to bind metal cation to form a very stable complexes. So the actually metal, when it is form complexes in the form of cryptand, then it is called metal cryptates. So uh, nowadays, in the academics as well as in the research or industry, so there is lot of and various applications of the cryptands. So because of the structural stability and its diversity, right? So the when we talk applications, so as you know that cryptand has multi cavity sites and multi-complexation modes and multi-cyclic rings. It can form cage-like structures. So it can form inclusion complexes. So because of the electrostatic interaction of the cation and electron-rich donor cavities, and so there are variety of complexes so that can be formed through the complexation behavior of the cryptand. And in the previous lecture, we have also discussed how we can um, tune the cavity size of the ring through the substituents. So we can change the cavity size through the uh, insertion of substituents in the exterior part of the rings, right? Or it can be tuned through the uh, number of increase of methylene groups. Suppose in the basic cryptand, so we have a two methylene groups. So we can increase one methylene groups. So ethylene groups can be replaced by propylene groups. So the cavity size can be also changed, right? And another way, we can increase the number of ethereal groups in the polyether segments or polyether strands. So then it will also enhances the size of the cavity. So as per the size of the cavity, so it has a high affinity or selectivity towards various uh, metal cations or anions or organic molecules. So depending on the structure of the uh, cryptand. Okay, so here we have extracted various applications. So for the cryptand and cryptates, so uh, that is the most important. So first application, it is actually in the field of organic chemistry. So preparative organic chemistry. So organic chemistry actually, there are a lot of organic reactions, so that involves the role of catalyst. So such type of actually metal cryptates can initiates or increase the rate of the reactions and uh, forms the products. So organic products can be uh, produced in the reactions through the use of this cryptand and cryptates. Third one is the solvent extraction. So solvent extraction, so it can extract the solvent from the mixture of the solvent. So because of the affinity, means it has a hydrophilic affinity as well as hydrophobic affinity. So the solvents which strongly loves the structure of um, cryptand, so they will be selectively extracted through the structure, and hence this is suitable medium to extract the solvent from the mixtures, right? And phase transfer catalysis, phase transfer catalysis, so actually it can uh, transfer the phase of compounds. So if suppose we have a ionic compound, so that is soluble in water, but it is insoluble in organic or any other non-polar solvents, so it can be transferred. So suppose we have a potassium chloride, so that is soluble in water but insoluble in toluene. So we can uh, increase the solubility in toluene of the ionic compounds. So it will help to solubilize ionic compounds in non-polar solvents such as benzene, toluene, and ethers. So by extracting the cationic part in its host, so once cryptand is added to the non-polar or organic solvent, so what happens actually, so it has a actually high affinity to extract the metal cation, so it will extract the metal cation from the uh, non-polar medium and solubilize the overall solutions, right? Solubility, stability of the reactive oxidation states. So some reactive oxidation state can be stabilized through the complexation effect of the cryptand, and it can also enhance or activate the anion, right? So once cation forms complexes with the um, cryptand, suppose uh, we have a cation, so cation, so that is suppose we have M plus cation, it forms um, so such type, suppose we have a cryptand structure, so it forms M plus so such type of a structure is formed actually, right? Here we can keep positive charge on the uh, complex. So this is called metal cryptates. So suppose we have a metal cation like KCl, right? So this is soluble in water, forming K aqueous plus Cl minus aqueous in the water, right? But this KCl, suppose we have a benzene or toluene, so toluene, so it does not forms ions, right? But formation of ions can be enhanced if we increase, if we add, suppose 222 cryptand, right? So the result is that this cryptand can, suppose this is the non-polar solvent cell in which there is a KCl, right? So this is non-polar solvent cell, non-polar solvent cell. So once this cryptand is added to non-polar solvent, the result is that this K plus and Cl minus is generated due to the polarization effect of the this cryptand structure. So what actually this potassium ion will be extracted towards this cryptand and forming such type of a complex where M plus, suppose that is K plus, and the resultant is 2 2 2, so that is K cryptand Cl, right? So this is positive and this is negative. So it has again positive charge on the cryptate and negative charge on the outer anion, that is chloride anion. So again this is a highly uh, ionizable compounds. So now this compound so remains in the this non-polar solvent as a ions, because now this non-polar solvent or toluene, so that is hydrophobic in nature actually. So it interacts the exterior solvation shell, that is hydrophobic rings, and they are not able to solvate this anion. So this anion reactivity or activity can be enhanced, and the the solution remains in a ionic phase. So in the non-polar solvents we can prepare ionic solutions. So ionic solutions can be prepared in the non-polar solvents. Ionic solution can be prepared in non-polar solvent, non-polar solvent, right? So because of the presence of hydrophobic structure or solvation cell, that that interact either via van der Waals force or dipole-dipole interactions or through the hydrogen bond or through any other uh, forces. So that will solvate this cations, and anions remains free in the exterior of the cryptate complex. So the mobility of the anions can be enhanced in this structure. Because of presence of cation and anions in the cryptate structure, so they can also act as a good ionic conductor. So ionic conductivity is due to the movement of the uh, cationic cryptate and anionic chloride ion. So, but in case of this ionic structure, actually, this chloride anion uh, is not effectively solvated through the nonpolar solvent such as toluene itself or the solvation shell of this cryptate structure. So the mobility of this chloride ion is faster compared to this complex cryptate structure. So the conductivity can be uh, found in the non-ionic solvents. So this is the beauty of the uh, metal cryptates, which is a ionic compounds, a special type of ionic compounds. Suppose we have potassium hydroxide, right? That is alkali, and we have KMnO4, right? So potassium hydroxide and potassium permanganate. So both will act as a ionic compounds in water or any other polar solvents, but these two species cannot act as a alkalis or oxidizing agents in nonpolar solvents. Suppose KOH, so, and this is the uh, plus, or suppose you have the KMNO4, right? So if you add these compounds in benzene, so this is your benzene. Benzene, the compounds is not soluble, right? And does not act as a alkali. Also, it does not act as a oxidizing agent. So because of the insoluble characters. So the solubility can be enhanced if we insert a pinch of actually cryptand. Then suppose we add cryptand to cryptand, right? So if you add cryptand in this reaction medium, what happens actually is that the potassium ion is extracted, and that forms K222 cryptand, right? And in the outer sphere it forms, this is plus MnO4 minus, or sometimes it forms K222 cryptand, right? So that is plus and OH minus. So more ionic species are present now in the benzene. So now this will act as a most important base or alkalis in benzene, and this species will act as a oxidizing agent. Oxidizing agent, and this will act as a alkalis, right? So this is the beauty of cryptand structure. So that actually enhance the oxidizing power and solubility behavior in nonpolar solvents. So because of the complexation effect of the uh, cage structure, so now this is called potassium cryptate as a cationic forms, and this is stabilized by permanganate ion, which is a anionic ions, counter ions. And similarly, this forms cationic cryptates, and now the counter anion is hydroxide ion. So because of presence of hydroxides, so this uh, uh, complex system will act as a basic or alkalis and oxidizing agents, right? So this is the beauty of cryptand structure, so that enhance the solubility of ionic compounds in nonpolar medium. Next one, it can help to create zintyl ions, J ZNTL, zintyl ions, right? So suppose SN5 2 minus, Bi5 2 minus, right? And we have various examples. So that example will actually help to understand the applicability of Bi4. So this is actually some examples we have noted of gentle ions, that is Bi4 2 minus Bi4. So this is your 2 minus. Now another one is SN5 SN5. So that is 2 minus lead Pb5 2 minus and SN9 4 minus. Te3 2 minus. Te3 2 minus. Sb7 3 minus. Sb3 minus 7. So these are called actually such type of ions are called gentle ions, right? So it has complex structure. So because of the self association or catenation property, right? So gentle ions are actually formed through p block elements. So in the p blocks I will discuss it in a very good or deep understandings. So suppose this is the bismuth